distribution. Let's say we have a set of Bernoulli trials. With our successes and the probability of success is B. And we want to define a random variable X. How did we define X for a binomial random variable? What? Number of successes out of n trials.
Yeah.
Here, we want to do the number of failures before our successes. Chris, you're right as well. We can formulate a binomial as the number of trials required to have our successes. It is the same as a geometric, where we defined it as a geometric distribution and we defined it as a first success distribution. So if you look at it from the perspective of a first success distribution, then a negative binomial simply is the number of trials required to have our successes. But this is the case that your book is talking about, so we're going to stick with this. So if that is the case, then X is supposed to have a negative binomial distribution with parameters R and B. Call it negative binomial. But before that, what should the support be for X? In other words, the possible values for X. 0 through R. Now, I see where you're getting the R from, Joe, but all I'm saying is I want R successes, but I'm counting the number of failures. In other words, is there a limit for the number of failures that I could have before having R successes? There isn't. So it's just 0, 1, 2, blah, blah, blah. It can keep on going, and it is a discrete distribution. A key thing about a negative binomial is very similar to a geometric, where we stop as soon as the arc success happens. So let's say you have R minus 1 successes. And that is the art success. The moment you get the art success, we stop. Good. Okay. Case by case, and then we could write the formula for it. Suppose I say R is equal to 4. Yes. Now, if R is equal to 4 successes, we are going to reserve 1 for the third, excuse me, for the fourth, right? So the fourth success is right here. The 3 other successes can happen over here. Yes. Let's say n is equal to 0. Which would simply mean how many failures? No. What? No. No. No failures at all. So we would have 3 successes. Great. If n is equal to 1, I have 1 failure, and I need to have 3 successes. So I don't want to write successes, I'm too lazy. And 3 successes. When the 4th happens, we stop. Good. So in total, how many trials do we have? 5. So 3, 4, 5. If n is equal to 2, I have 2 failures, 3 successes, and then the 4th success. And when it happens, we stop. Good. You see where I'm going, right? Or do you not see? No. N is equal to 3. Three failures, 3 successes, and then the 4th success happens. Good. And I can keep on going, dot, dot, dot. Because I can go all the way up to 100, and you'd have 100 different failures, 100 failures, and then you'd have successes. In total, though, prior to the 4th success, how many trials do we need? In terms of n and r. So here, what? Very good. So here it is r minus 1. N is 0. N plus r minus 1. Still r minus 1. N is 1. N plus r minus 1. R minus 1. N is 2. N plus r minus 1. So in total, the total number of trials we have is simply n plus r minus 1. Do I desire that the failures and successes happen in this manner? No, it could happen in any way, right? So in how many ways could I put those r minus 1 failures, or excuse me, r minus 1 successes in here? Do you follow the question? So I have 3 successes, instead of saying, do I desire the failures, do I desire that my successes always fall the way I wrote it? And you guys said, no, not necessary. So in how many ways can I throw in these successes here?
N plus r minus 1 choose n.
N?
No.
The number of successes, I'm not looking at this.
R minus.
R minus 1, right? So the number of ways to place or to have r minus 1 successes in n plus r minus 1 possible trials is n plus r minus 1, and we choose r minus 1. Does that make sense? So all we have done so far is come up with a number of ways in which I could put those r minus 1 successes. Earlier I mentioned in a way, negative binomial random variable can be defined as x, where x is the number of trials required to have our successes. Yes. So if I just change this to n+1, or I started with some arbitrary m, the failure bunch of successes eventually will tell me the number of trials required to have 4 successes. Do you agree? So that is the other version of a negative binomial. Your book does the number of failures. So initially, how many how many successes we know we have prior to the odd success? R-1. N is the number of failures. So Q is the probability of failure. So I can write it as Q raised n-1. And then your last success happens, and that last success is simply the odd success. So another success follows. So what is the probability of that? Huh? 1. With what probability would that success happen? B, right? It's not a certain event. It happens with a probability. So times B. I just didn't want to simply write the formula. I wanted to explain as to why the formula it is the way it is. So R-1, so we would have P raised R multiplied by Q raised N. We have a 6-sided die, and I need to know the number of times I have to fail in order to get 6 successes. The moment I get the 6th success, we stop. So we're not going past that. So if that is the case, what is the probability that exactly 4 failures occurred so that I have 6 successes? So the probability of a success is volume 6. Which is 1/6, and that would be P. So if P is 1/6, Q is 5/6. What is the distribution of X? Huh? So the probability of X is equal to 4 is simply N, which is 4. The value of R, 6, minus 1. R is 6, minus 1. P raised R, 1/6 raised 6, multiplied by 5/6 raised 4. And That is 9 choose 5 multiplied by 5 raised 4 over 6 raised 10. There is a 13 in 10,000 chance that would happen. Very small probability. Do we follow? So now do you see the connection between what I mentioned at the very beginning of a negative binomial? So even though I defined the negative binomial as the number of failures required in order to get 6 successes, I can change the wording of the problem and still have it as a negative binomial. So we have 64 trials and I need 6 successes exactly. So 5 successes, that's the 6th success. And in total, I would have 64 trials. So I have accounted for 5 trials plus 1. That would be 6 trials, which would leave 58 trials, and all of those 58 must be failures. Do we agree? So we have 58 failures. And that we can go back to our negative binomial. Still, it is negative binomial 6 and 1 over 6 because I didn't change that. So the problem now becomes probability of x is equal to 58, which is 58 plus r 6 minus 1, r minus 1, 1 over 6 raised number of successes, 6, and 5 over 6 raised 58. And what do we get? 0.0039, just 3 times the probability of the last. That's a lot of failures, right? But does this small probability make any sense? Sure, because I'm looking for an exact value. If I did at least or at most, perhaps I'll get a slightly higher value of probability. Are we clear? Okay. Is to use the linearity of expectation. What is a geometry distribution? Not the first success distribution, the geometry distribution, like the way we define it.
You can only have success or failure.
True. If x is geometric P, what does it measure?
It's, I guess, the first success is the number of failures.
Right, the number of failures I need before the first success. That's how I define geometric. Good. We know the expectation of geometry. We derived. What is the expectation of geometry? This case, not the first successful one, expectation of geometry. So, and also we know expectation of x is 1 minus p divided by p, right? When we formulated the first success distribution, it was simply the number of trials required to get the first success. The probability, the expectation there was simply 1 over p. Yes. So here we want the number of failures prior to the first success. I'm going to extend this to a negative binomial to find the expectation. So suppose y is negative binomial or common p. Now, how do we write a negative binomial in terms of something that's easier so that we can find the expectation? Keep in mind, that's how a statistician thinks, to take a distribution and write it in terms of another distribution so that you don't spend too much time. Yes.
Well, if it's the number of failures for the first test of geometric, then it's R just one. Like if you had a negative binomial function for R is one, that's just half.
That is very correct. So now extend the idea, Andy. No.
Oh, well, Andrew. So
Andrew, okay. So if you extend the idea, you're correct. So if R is 1, we're just talking about a geometric distribution. So if R is not 1, what is the logic behind it?
Subtract all the way until you get to 1.
Subtract all the way until you get to 1.
Yeah. You got the geometry.
Okay, think the other way. You're building up to R, right? Right, you're adding all the way up to R. Let's say you keep on going until you get the first success. Yes? So the geometric stops right there. And then you start at the next trial. So you start right there and you keep on going. You get the second, you see the adding part. So you get the second success. You start over here, keep on going, you get the third success. Dot, dot, dot. Somewhere over here, and you get the odd success. Yes? So until the first success, this would be geometric. Do you agree? Because as Shay mentioned earlier, we have only 2 choices per trial, which would make it a Bernoulli experiment, which would satisfy the condition for geometric distribution. So we have x1. And you come here, what is the distribution of that? It is still geometric. So even if I asked you, well, what is the probability it is going to take more than 2 trials? It is the same as saying, you know, or starting from here. It is like you reset and you begin from here. That is what we call the memoryless property of geometric distributions. There is only one continuous distribution that will satisfy the same thing, and that is exponential. We will talk about that when we get to continuous distributions. So this step, what would the distribution be here? Geometric. And I need R successors. What about the last one? And if I want to find the total of all of them, what should I do? Add them all together. And all of these xi's are geometric P. We know the expectation of geometric P, we derived it last time. So expectation of y would simply be equal to expectation of sum of I equals 1 to R xi. Good. Linearity of expectation simply states that if you have sum of xi, has to be sum, not product. If you have sums of random variables, you can pull the sum out and simply add their expectations. So I equals 1 to R, expectation of xi. Since all of them are geometric P, the expectation here is simply 1 minus P divided by P. So and what is the final answer?
R times that.
R times 1 minus P over P. Well, now this makes sense to going back to what Andy said. Well, if I just plug in 1, it becomes a geometric. Very true. If R is 1, we get the expectation of a geometric random variable.